Carissa Blossom, who came from the production engineering team of the Eats and Deliver part of Uber. Excuse me, Carissa, I'm really tired at this point. Okay, let me try this again. So Carissa is a member of the production engineering team for Eats and Deliver at Uber. She's also an incident commander during critical outage mitigations. And today we will be learning from her how she helps Uber become better at handling these incidents. Carissa, I'm sorry again for butchering this. The stage is yours. Have fun.
All right. Hi, guys. Today, I get to talk to you about one of my favorite subjects, outage mitigation. I'm going to take you through Uber's growing toolbox for managing major user-facing outages. But first, just a little bit about me. My name is Carissa, as Akos mentioned. I have been an infrastructure engineer at Uber for over 4.5 years, focusing primarily on production reliability and SRE work. I spent 3 of those years as a commander on Uber's elite outage mitigation squad. I'm currently working on scaling Uber Eats and delivery reliably. Now, in case you're wondering, that's me. Having spent the last few years training incident commanders for Uber's outage mitigation squad, I can say with a fair degree of experience that the best way to learn about how Uber manages outages is to experience one. So I'm going to start by giving you guys a sneak peek at an Uber outage. Let's pretend that you're me for the day. Today, you are the incident commander, and your job is to respond to critical user-facing outages and manage them through to resolution. So that's where we're going to start, with a PagerDuty page. Congratulations, folks, you got paged. So what exactly does our PagerDuty page say? 50% of Uber rides and Uber Eats requests are failing in the 5 biggest cities running out of data center region A. Now, we're quickly going to dig a bit further, and from our observability tools, it looks like we can see that all of the smaller cities are unaffected, and our second data center region looks fine. But an increasing percentage of requests to our 2 main apps in all of the biggest cities, right? The 5 is now increasing rapidly, that are running out of data center region A, they're all failing. But what exactly is data center region A? And what does it mean that cities run out of a specific data center? Let's quickly go over Uber's city sharded architecture. Uber has 2 data center regions with 3 zones running inside each region, some cloud and some bare metal. Trip requests from users are sharded by city, meaning that cities are associated with and run specifically out of a given data center region. Most services are deployed to 1 or more zones in each region, and all must actively operate out of both regions. To give you a simplified version of the upper part of our stack, traffic from your mobile phone routes via DNS to one of Uber's domain addresses before entering one of Uber's regional data centers through our data center front-end servers. Most requests are then routed directly via Nginx to our business logic gateway. Our configuration management system stores the current regional placement of cities. The business logic gateway leverages this information from the config manager to route requests to the appropriate region. Now, keep in mind that these cities and their placements are just examples. But let's say that a request from a user in New York City is routed to the gateway in data center region A, the wrong region. The business logic gateway will automatically issue a 307 status code and redirect the request to the correct data center region, region B. So the last information you're going to need to understand that page you just got is how deployments work at Uber. In addition to service-based rollouts, Uber has 3 different processes for rolling out different features or product configurations. These changes are rolled out not just by engineers, but by operations team members in cities all over the world. And they're rolling these changes out on the city, zone, regional, and global levels. Service deployments are at the core of our reliability challenge, causing over 60% of major outages. Now, Uber has no particular structure or process around who can deploy what service or when, besides a strong encouragement that service owners deploy slowly and incrementally across zones, starting with a canary zone and hopefully preceded by a staging rollout. Service deployments at Uber use a ramped rollout strategy, starting with a canary zone. Manual user acknowledgement backs up automatically generated alerts to ensure that, at least theoretically, outages are caught well before they reach the second data center region. Even if an on-call engineer isn't paying enough attention, automatically generated alerts track the ongoing deploy and automatically roll back deploys if there is an issue with a deploy in a given region, as you see here with the high CPU alert rolling back the deploy in zone 2. So let's go back to our outage. An increasingly large majority of Uber rides and Uber Eats requests are failing in what is now all of the biggest cities running out of data center region A. This is major. We are all hands on deck. So what are we going to do? Let me break the bad news to you first. This is not going to be an easy one. Nobody has jumped onto the central outage Zoom to let us know that they deployed something problematic, which is already rolling back. We're just on here with a bunch of panicked people, but nobody has any solid theories about which service is actually responsible. Not to add any pressure here, but the clock's ticking. And while you think about exactly how to resolve this outage, on average, Uber loses over $100,000 per minute in these major outages. And it's more than just money that's lost. Consider the damage to our brand's reputation, the possible regulatory or compliance agreement violations, the loss of trust by customers, many of whom are relying upon us as their livelihood and their form of transportation. For that reason, our elite outage mitigation team holds ourselves accountable to a special internal-only SLA. These critical outages that we get paid for have to be mitigated within 10 minutes. So how do we figure out what is actually causing the issue, or at least mitigate any impact to users in 10 minutes flat? Think quick, because you've actually only got about 9 minutes left now. Let me give you a clearer picture of how big of a challenge it is to find the needle in this proverbial haystack. Uber has over 4,000 microservices, owned and maintained by thousands of engineering teams. These teams initiate over 300 service deploys an hour, with the average deploy taking over 4 hours to complete, and larger, more critical services taking up to 1 day. In addition to this, these engineering teams, as well as operations teams around the world, are making over 1,500 configuration flag changes per hour, not to mention the thousands of experiments that are being rolled out in the same time frame. That all adds up to one big haystack that we're hunting in. But wait a minute, why do we even need a central team for this? Why are we searching the whole haystack at all? I get that there are thousands of services and thousands of teams, but can each individual team just fend for themselves and manage their own outages? I mean, why is it taking so long for whoever is responsible to realize that they are at fault? Seems confusing, especially given the slow, safe deployment process, complete with targeted alerts and automated rollbacks. Here's the thing. Theoretically, yes, service owners should catch any outage related to their service right when it starts to happen and just take action. And they often do. These service deployment automated rollbacks do catch a lot of issues, but not all issues are so clear-cut as to be clearly derived from a single service. As much as I'd love to say that our alert coverage is 100% complete and catches every possible issue, the reality is a lot more like Swiss cheese. No matter how well we design our systems and processes, no matter how well service owners prepare and plan, outages still happen. Information is highly distributed, and reasoning about the thousands of changes that are simultaneously going out is hard. Adding to the chaos is the challenge of coordinating the many changes that could be causing a major outage of this kind. Keep in mind the sheer number of services that are releasing changes simultaneously. Without coordination, a group of really smart people may all try to take charge and waste time trying to decide who is actually best suited to be in charge. Or they may assume someone else is handling the problem and do nothing. Back when I first joined Uber in 2016, there used to be an introduction class where a senior engineer would whiteboard out the entirety of Uber's core flow architecture by hand. It took an hour. The guy never stopped talking. He never stopped writing. No single person at Uber today could accomplish this task. Doesn't matter how much time you give them. One of the key facets of Uber's central mitigation team is to try to fill this gap, to be trained and regularly retrained with a high-level understanding of Uber's entire core flow architecture on a high level for our main products, so that when these outages happen, we can step in as the clear leaders with the knowledge and the training to coordinate the many possible root causes and the multitude of impacted services to bring an outage to an efficient, organized resolution. But back to our outage. So thanks to this extensive training that we went through as incident commanders, we know that there are only 10 possible services that, if degraded, could cause Uber Trip and Uber Eats requests to fail. So first step, we're going to page these 10 on-call teams to have them join our outage soon. Luckily, they're all very good at their jobs and immediately jump on the call. 4 of these teams on calls inform us that they were rolling out a change in the approximate time window that the outage occurred. Each team ensures us they took all of the appropriate steps to prevent a potential outage from happening. All their pull requests that were included in this deploy were stamped by at least 2 engineers, included passing unit tests and integration tests. It was deployed first to staging before rolling out in production. And all 4 deploys are well past the canary stage. None of these teams are receiving any alerts that suggest they are anything except victims. So are we missing something? Is one of the other 4,000 teams responsible? Are one of the on-call engineers missing something? Think fast. 8 minutes now to figure this out. I'll take mercy on you and break the news. We're not going to be able to figure out this issue in time. If you are expecting me to unveil some kind of magic software that we've developed to root cause major outages in highly complex systems in 10 minutes flat, you clearly didn't read the speech title. Debugging and root causing an outage like this could take hours. It's time we don't have. So we're not even going to try. Let me break it down for you. The good news and the bad news. I like to start on the bad news because then we end on a good note. First, we don't know what caused the issue. We also don't know what deployment mechanism rolled out the change. And we don't know how long it's going to take to resolve. But we know when the issue started, and we know the scope and the severity of the issue. And this is the key here. This means that we know that the issue is isolated to a specific region. It's only affecting big cities running out of data center region A. And with just this little bit of information, we already have enough to mitigate the outage. So to recap, given the number of different services that deploy simultaneously, the potential for an issue to be not with an individual service, but the interaction between new code from 2 different services, and the fact that our production integration testing looks at and alerts on Uber apps flows as a whole, we often don't know what particular services changes cause an outage. And we can't just sit there and hope that the service on call figures it out. It's far too costly to the business and, more importantly, to customers. So we reach into our toolbox for our most valuable outage tool, the marketplace failover, fondly referred to as the big hammer. Why do we call it that? Because it moves everything with a little bit of damage. I'll show you how. So before we actually use our hammer, we have some prep work to do. We need to lock things down. Our central outage mitigation on-call engineer, remember, today that's you, is going to leverage our outage mitigation CLI tool to pause our service deployment and configuration flag management systems. This protects working regions from bad changes. It also ensures that no new changes can roll out while we are running out of a single region. It's too much risk. So how exactly does this hammer work? Our marketplace failover uses our outage mitigation CLI tool to update city placements in our configuration management system. Once updated, our configuration management system tells our business logic gateway in the problematic region to start redirecting traffic to the other data center for processing. All cities now run out of one regional data center. So as we can see here, the business gateway issues the 307 redirect from the drained region A to region B because config manager tells it that all cities are now running out of region B. This means that all of the downstream services are also only running out of data center region B. So why are we doing this? Why fail everything over? First, it allows for the mitigation of a major outage within minutes, as long as the issue is scope 2, at most one data center region. Second, on-call engineers don't need to know what caused the outage. You can hold off on investigating root cause until after mitigation. Put simply, mitigating first and root causing second significantly reduces the user impact of major outages. If you're not yet convinced, consider this. Even in those cases where the on-call engineer from the responsible team does know that their service is responsible and takes action automatically or manually to roll back the problematic deploy, the average deploy takes over 4 hours. More critical services with a large number of compute instances per data center region take a lot longer, with some services taking a full 24 hours to deploy. A standard rollback takes the same amount of time to roll back as it did to roll out, since each host has to be redeployed with the old safe version. Even in an emergency rollback, our fastest option for these kind of urgent outage scenarios still takes a lot of time. We still have to keep a large enough percentage of instances running the old problematic deploy to handle incoming requests. So we can't just update all of the hosts at once. Even when we know the root cause, we often still need to mitigate while we wait for the outage to resolve. So clearly, the hammer is an amazing and it's a great tool, but we call it the hammer for a reason. This thing can do some serious damage. First, there's the productivity impact. Locking down and failing over all services hinders engineering productivity for many hours. No backup region means it's not safe to deploy new code. Second, it puts strain on the entire system, which needs to now be able to handle peak load out of one region. Otherwise, the mitigation might lead to an outage in and of itself. Third, this stress test that it puts on the system forces services to maintain significant capacity headroom to support this failover load. And finally, given all of this potential risk and the challenge of making the call of when it's safe to revert to normal, we had to create and maintain this specially trained on-call team that today you are a part of, that knows when and how to execute the failover and how to manage the overall outage. Remember those 10 services that we mentioned earlier? The 10 that all deal with the centralized supply demand functionality common to both the Uber Rides and Uber Eats business? Well, Now that we're mitigated, let's look at actually what happened with them. It turns out there's a shared Redis cache that many of these 10 services use. One of the 4 services that was deployed during the time frame included a configuration update for this shared path that attempted to avoid using event loop threads for miscellaneous non-IO operations. Unfortunately, there was a bug in the pool configuration that only presented itself in high volume cities, where all of the requests got blocked when there were no connections available. Unfortunately, there were no alerts set up to track the number of threads used. And while the number of session links did have an alert set up, the alert threshold was so high that it didn't fire until 35 minutes into the outage. Since we were already mitigated by then, and given the alert triggered so long after the outage began, no one actually considered it as a potential root cause until several hours later. So we really were saved by the hammer. Getting to the root cause took over 4 hours. Had we waited until we reached root cause rather than mitigating first, the deployment would have reached both data center regions, effectively taking down Uber Eats and Uber Rides business. Instead, thanks to our failover tool, we were able to mitigate in about 20 minutes, saving over $4 million. But what about the pain and the cost associated with those big hammer failovers? Surely Uber can come up with a better way to do this. So let me introduce you to the newest tool in Uber's mitigation toolbox, the Scalpel, better known as the Muttley drain. To show you how we built this next tool in our outage management toolbox, I'm going to have to introduce you to a central aspect of our networking stack. Muttley is a modern zone-aware forwarding proxy developed at Uber, which is deployed on all production compute hosts. It performs automatic load balancing of inter-service traffic and supports HTTP and gRPC, as well as our internally developed protocol. It automatically routes around unhealthy instances and reports and leverages reports by our distributed health checking service and our traffic policy service to determine which zones a service is running in and distribute load between instances in these zones. So let's say that service A wants to send a request to service B. Muttley pulls service B's host list using our discovery service and discovers that service B is running out of the same zone in data center region A as service A. And its traffic policy says that you want to send the request to the nearest zone. So it leverages service B's traffic policies and health states of instances from that host list to route the request directly to an instance of the destination service. So what does Muttley have to do with this mitigation tooling? Well, the Scalpel, or the Muttley drain, leverages Uber's networking stack, particularly Muttley, to remove zones from the list of routable destinations for a given service. Our Scalpel basically updates the traffic configuration for a given service so that when Muttley goes to actually send the next request bound for the service experiencing an outage in a given zone, Muttley thinks that the drain zone has no capacity. There are simply no instances there. As far as Muttley is concerned, the service does not run there, and the service is thereby drained from the affected zone without any other service being touched in any way. Let's look at an example of how this would work. Remember those 4 services that were all possible culprits for our outage? All 4 could, if degraded, cause Uber trips and Uber Eats order requests to fail. And all 4 were rolling out a change in the approximate time window that the outage started. So let's say that instead of executing an entire marketplace failover, we just decided to Muttley drain those 4 services. Let's pretend that one of these services is called foo. We can use Muttley and the underlying network control plane to drain the service from all of the zones in the problematic region, region A. By essentially removing those zones from the list of routable destinations for Motley to send requests for service foo 2. So region A's zone 1 and zone 2 essentially cease to exist for services trying to reach foo instances. So Motley will then naturally route traffic from any of the regions to the next healthy outage-free foo instances, which now happen to only be in region B's zone 3 and zone 4. And we can do this on a zonal level as well, removing a single zone instead of all of the zones in a region. This is a big advantage over our marketplace failover hammer, which can only operate on a regional level. Even if only one of the 3 zones in a given region is impacted in a particular outage, the marketplace failover requires the failover of the entire region. So let's look at how this new tool of ours stacks up against our big marketplace failover hammer. On the positive side, other services continue to run out of all zones and regions. So no engineering-wide lockdown is required. There's no reduction in productivity for unrelated teams. There's no stress testing of unrelated teams, and thereby no potential outage from those unrelated services having insufficient capacity. All of this means that there is less risk, which means that we don't need a specialized team to run these drains. Service owners can just do this themselves. It's also a lot faster than the big hammer. While the hammer can take up to 10 minutes to complete, Motley drains finish in seconds. But there are some serious weaknesses. This only works when we do know what service or group of services is likely responsible for the outage from the start. And remember, we still have to get there in 10 minutes flat because we have that internal SLA. So given how complex our systems are, we still find ourselves struggling to narrow down the likely culprit fast enough to use the Scalpel instead of the big hammer. But while our Scalpel may not allow us to completely replace the big hammer, it turns out they work really well together. Big hammer failovers are still incredibly valuable for quick outage mitigation. When we don't have a short list of possible culprits within our SLA, this is undoubtedly our best option. If our culprit list proves wrong and our Motley drains don't mitigate an outage, this is still our tried and true fallback solution. That said, Motley drains do replace a lot of big hammer use cases. Our central mitigation team doesn't need to use our big hammer when a critical service has a bad deploy that the service owners caught themselves within the first region. The service owner just drains via Motley the service themselves to the unaffected region. And as time goes on and teams gain confidence in our Scalpel and learn how to also effectively broadcast necessary communications to other teams, the central outage mitigation team has to step in less and less frequently. In those cases where we're still doing big hammer failovers first, Motley drains still provide a lot of critical support and dramatically increase our reliability. Let me tell you how. First, Motley drains can help reduce the amount of time we have to actually stay in a full big hammer failover. Once you know what services are responsible, you can Motley drain those services, then revert the big hammer failover. So other teams then get to go back to work while the root cause services issues get resolved. Second, Motley drains can help prevent secondary outages from capacity overloads in unrelated services. So we can use Motley drains to force healthy services to run out of both regions to balance traffic and prevent insufficient capacity causing a second outage. And third, Motley drains can also help mitigate 2 outages in opposing regions, even when it's not just insufficient capacity. If a secondary outage occurs in the region that we are now completely failed over to, due to some other issue, we can take that specific service and drain the service responsible for the second outage to the first region. Oh, sorry. But what about with our specific outage? Could it have helped? So not every facet of Uber's architecture is connected via Motley. Kafka-based services or data stores, like the Redis cache in this outage, don't use and therefore can't be failed over by Motley. We can't fail over the cache itself. However, while the service owners of the 4 suspect services at the beginning of the outage were right that their service was not responsible, we still could have essentially mitigated a majority of this outage and its user impact without the marketplace failover had we Motley drained these services to the opposite region, since they would have then been using the healthy Redis cache in the opposite region. Granted, there were a few other services besides these 4 that also use the Redis cache that were not actively deploying, and they would have still been experiencing problems after we executed those drains. So this is where it comes down to the call of the particular incident commander. It would have been relatively easy if you put this together fast enough to just drain those few other services that were still alerting and experiencing problems in data center region A, while leaving the other 4,000 or so services happily running out of both data center regions. But even if, instead of draining the other impacted services, the incident commander decided that we had not actually found the root cause, since there were still impacted services running in our problematic region, and decided to go with the big hammer failover, the safe tool. Motley drains would have still been helpful in dealing with the strain on other services during this outage. One of the Uber Eats core services did struggle with insufficient capacity headroom while we worked to root cause for those 4 hours. And had we had Motley drains at the time of this outage, it could have helped prevent the degradation of that particular service. So where do we go from here? First, no matter how strong our mitigation tooling, it's always better to just not have outages in the first place. We're working on improving our testing processes and creating safer rollout strategies to catch outages before they happen. Second, we're working on taking a high-level overview of our observability stack to figure out how to fill gaps in our alerting and enable us to narrow down the likely culprits of an outage faster to increase the opportunities to use Motley drains instead of big hammer failovers. Third, we're working on automating the use cases for big hammer failovers in those cases where we know for sure that this is the best option and there isn't a choice to use the Motley drains. If we can find ways to automate that, again, we can significantly reduce our time to mitigation. And finally, we're working on automating Motley drains as well, particularly as a further automatic trigger action when deploys automatically roll back to reduce our time to mitigation and prevent user impact almost entirely, since it happens in seconds during the rollback process. So you may be sitting there with a much greater appreciation of your Uber app, but otherwise unclear on how this applies to your life. In response, I offer you these general lessons that we learned the hard way for effective outage mitigation so that you don't have to. First, don't allow any change to roll out everywhere at once. Second, lock down systems to prevent further changes from rolling out during an outage. Third, ensure clear communication and efficient decision-making by having a single experienced person in charge during the outage. Fourth, have a system for keeping track of what changes or deploys happen and when. Make sure it's really easy to search and filter based on a given time frame. And most importantly, I think it's critical to keep emphasizing this one because as engineers, it goes against our natural propensity for problem solving. Mitigate first, resolve second. Thank you very much for your time. Please feel free to reach out via my LinkedIn if you have any questions. And if you are inspired by what you've learned today and want to learn more about Uber's engineering practices, check out our engineering blog. or if you're really inspired or really enjoyed this talk and think that these are the kind of problems that you love solving, we're hiring. So come and join us at Uber. Thank you for your time.
Thank you very much, Carissa. It was a very awesome talk. And we actually have a couple of questions in the Q&A section. So if you don't mind, we get started with this.
Give me 1 second. My laptop is about to die. I'm going to just grab my charger.
Absolutely, no problem. Meantime, I can maybe sing a lullaby or not. Unfortunately, I don't have more Yoda jokes for you from today. All right. We're not dying anymore. That's awesome. Outage mitigated. All right, perfect. So our first question of the day is going to be, do you have some mechanism in place to quickly roll back services to a specific version in time?
Do we have a mechanism to roll back to an older version automatically?
Yes.
Yeah, we do. So basically when we have our own internal deployment service that we've created. So unfortunately, this isn't an open source tool that I could just share with you guys how we're using Spinnaker, for instance. But it's pretty similar though. Essentially, we have a bunch of alerts, and all of the ones that every service should just always have by default. Those alerts are automatically generated and tied to deployments. So the high CPU alert, for example, or like 5xx errors. So when a deploy is rolling out, it knows the new version, but there are still a lot of instances that are running on the older version. And so the deployment system is aware of what to roll back to, and it still has that build available. So if an alert goes off in the zone that's deploying, so our zone 2 high CPU alert, and it's like, whoa, like your CPU has just like skyrocketed through the roof. Like there's clearly something wrong here. Like you need to roll this back. It doesn't wait for the user to like receive the automatic page and then take the action themselves. The deployment system itself starts to roll back, and it's going to go to the older version that it was deploying from. So that's how that works.
Okay, thank you. A bit related question to this. Are your teams investing into reducing deploy times?
Reducing deploy times. So this is actually an interesting conversation that we have on a regular basis. There is an essential trade-off between the time that it takes to deploy, which helps with greater efficiency, right? You can get out more code changes faster, and the reliability. And so what we're starting to move towards is we have a secondary deployment service called UCD, and it's basically continuous deployment. And so certain services will choose to use that. And then the same process still applies. So in that case, those tend to cause a lot fewer outages, but there are a bunch of different trade-offs that determine why a service may choose to use UCD as opposed to the standard process. But part of this really comes down to the fact that Uber has made this choice, for now at least. We continuously investigate blue-green as an alternative, for example. But a lot of these trade-offs that we face have to do with the fact that we have made this call to use ramped rollouts. So rollbacks are not instantaneous like they would be in a blue-green model. Hopefully that answers your question.
Hopefully it does. It definitely
If not, just reach out on LinkedIn and you can give me a hard time and I'll answer it properly.
Awesome, thank you. We have one more question in the Q&A section. Why did you choose Go as the implementation language for the Scalpel?
Good question. So Uber's made a decision a couple of years ago, I think 2017. We have certain supported languages, and pretty much all of our stack runs in them. Ours are Go and Java. Writing this in Java would be extremely painful, so we went with Go.
Okay, that's an easy answer. Thank you so much. Yeah, I wouldn't start
I
writing.
wouldn't write this in Java. That would be so painful.
Yeah, my teams are mostly working in Scala and TypeScript. So yeah. Okay. I don't see any more questions popping up. So I guess if you people are shy asking questions from Carissa, you
Last thing, they're probably tired.
Yeah. Yeah. She offered kindly to bug her on LinkedIn. So please do that then. And Carissa, thank you so much for your talk. It was awesome.